A sudden spike of radio noise screams across the cosmos. For just a few thousandths of a second, a flash of energy brighter than 500 million suns erupts in the darkness. This is a fast radio burst, one of the most baffling signals we have ever intercepted from the depths of space. By the end of this exploration, you will know the 25 strangest discoveries that have transformed these flashes from a scientific curiosity into a profound cosmic mystery. We have tracked them to tiny, chaotic galaxies and caught them repeating on a precise schedule. We have even detected one from inside our own Milky Way, linking them to the universe's most magnetized monsters. What cosmic engine can possibly fire off more energy in a millisecond than our Sun produces in 80 years? And could these bursts, in their bizarre regularity, be trying to send us a message we simply cannot yet decode? The story of fast radio bursts is a detective story written across billions of light years. What do you think is waiting for us at the source of these impossible flashes? The mystery began not with a live alert, but with a ghost in the machine. In 2007, astronomer Duncan Lorimer and his student David Narkevic were sifting through old recordings from the Parkes Radio Telescope in Australia, data originally gathered to study clouds of gas around distant galaxies. Their goal was routine, a kind of cosmic archaeology, but buried in that static, they found an anomaly so powerful it defied all expectation. It was a single spike of radio waves lasting just 5 milliseconds, a blip so brief you would miss it in the blink of an eye. Yet the energy packed into that instant was staggering. Calculations showed that in that flash, the source released as much energy as the Sun does over 80 years. The data plot was iconic, a single, towering spike erupting from an otherwise flat line of cosmic noise. The most shocking part was its origin. Based on how the signal was dispersed, stretched out by the thin gas between galaxies, they realized it had come from far, far beyond the Milky Way. This was the first fast radio burst, later named the Lorimer burst. The initial reaction from the scientific community was profound skepticism. Many thought it had to be a glitch, an earthly interference, or perhaps a malfunction of the telescope itself. A single, unimaginably powerful event from deep space, it seemed too extraordinary to be real. Yet that solitary spike in the archived data was the first clue, a single footprint left by a cosmic giant. It whispered that the universe was hiding a phenomenon more violent and enigmatic than anyone had dared to suspect. That single, ghostly signal demanded an answer to one crucial question. Where did it come from? The Lorimer burst was a cosmic scream, but was it a nearby shout or a distant roar from across the universe? The key to unlocking its origin lay hidden within the signal itself, in a property called dispersion. Think of it like this: when you throw a handful of pebbles into a pond, the bigger, slower ripples arrive at the shore just a little after the smaller, faster ones. In space, something similar happens to radio waves traveling through the thin, scattered gas between galaxies. The lower frequency waves, the deeper cosmic notes, get slowed down more than the higher frequencies. The result is that a sharp, simultaneous burst gets stretched out into a descending chirp by the time it reaches our telescopes. The greater the stretch, the more intergalactic gas the signal has traveled through, and therefore the farther it has come. When astronomers measured the dispersion of that first burst, the numbers were staggering. It pointed to a source not within our Milky Way, but far beyond its borders, in the deep, dark ocean of intergalactic space. This was the monumental second discovery. Fast radio bursts were not local phenomena. They were extragalactic, some erupting from mind-bending distances of billions of light years away. That calculation transformed everything. It meant the energy required to produce a flash bright enough for us to see from that far away was almost incomprehensible. Whatever was creating these bursts had to be a cosmic engine of unimaginable power, capable of focusing more energy into a millisecond than our Sun will emit in decades. The universe, it seemed, was filled with invisible titans, occasionally flexing a muscle so violently we could detect the echo across cosmic time. For years, the leading theory was a grim and final one. Astronomers suspected these brilliant flashes were cosmic death cries, the final catastrophic moments of unimaginable events. Perhaps a neutron star collapsing into a black hole, or two incredibly dense stellar corpses smashing together in a final, fatal embrace. These were one-time cataclysms, universe-shattering fireworks that left nothing behind but a fading echo. That assumption was shattered in 2016 with a discovery that rewrote the rulebook. A burst designated FRB 121102 did something extraordinary. It flashed again and then again. Over many months of observation, the same precise patch of sky kept lighting up with these powerful millisecond bursts. This was the third and perhaps most pivotal strange discovery. Fast radio bursts could repeat. The source was not destroyed. It lived on, capable of firing off these titanic salvos of energy over and over again. This simple fact eliminated entire categories of explanations. You cannot have a star explode twice. You cannot have two neutron stars collide, then somehow reassemble and collide again. The repeating bursts meant the source had to be an object that could survive its own outburst, a cosmic engine that could reload and fire repeatedly. Suddenly, the spotlight turned toward the universe's most magnetically charged monsters, objects like magnetars. These are the super-dense, spinning cores of dead stars, possessing magnetic fields so intense they could strip the information from a credit card from halfway across the solar system. A magnetar undergoing a starquake on its unbelievably hard crust could theoretically unleash a blast of energy that fits the profile. It could survive the event and do it again. The repeater transformed the mystery from a search for corpses to a hunt for a living, breathing, and deeply temperamental beast. If this object could fire at will, what was triggering it? And was it alone, or were others out there waiting to reveal their cyclical nature? The discovery that a burst could repeat was a game changer, but it presented a new and urgent challenge. We had a cosmic engine that was still running, but where exactly was it hiding? Pinpointing the home of the repeater, known as FRB 121102, became astronomy's greatest treasure hunt. The breakthrough came through a coordinated global effort using a network of the world's most powerful eyes on the sky. The key instrument was the Very Large Array, or VLA, a sprawling collection of 27 radio dishes in the New Mexico desert that worked together as one colossal telescope. Its incredible resolution allowed astronomers to do something unprecedented. They caught the repeater in the act not just once but multiple times. With each flash, the VLA narrowed down its location with breathtaking precision. This data was then handed off to optical telescopes like the Gemini Observatory in Hawaii, which scanned that tiny patch of sky for a visible counterpart. What they found was the fourth strange discovery, and it was utterly unexpected. The home of this furious, repeating cosmic beacon was not a majestic spiral galaxy like our own Milky Way. It was not a quiet, elderly elliptical galaxy. It was a tiny, faint, and chaotic dwarf galaxy, more than 3 billion light-years from Earth. This unassuming speck, barely visible against the cosmic dark, was the powerhouse. This environment was a vital clue. Dwarf galaxies are cosmic relics, often described as metal-poor, meaning they contain fewer heavy elements forged in stellar furnaces. They are also frequently sites of frantic star formation, chaotic nurseries where new stars are born in turbulent clouds of gas and dust. This told astronomers that the source of the fast radio bursts was likely linked to a young and extreme stellar population. Perhaps it was the remnant of a massive, short-lived star that died a violent death in this fertile environment. The fact that such a modest galaxy could host such a titanic phenomenon forced a complete re-evaluation. It suggested that the conditions for creating these bursts might be more common in the universe's smaller, more primitive building blocks. pointing toward a progenitor that thrives in cosmic chaos rather than galactic order. For decades, the hunt was focused on the distant cosmos, but the answer was waiting in our own galactic backyard. In April of 2020, a known object within the Milky Way, a magnetar called SGR 1935+2154, suddenly woke up. It had been a known source of occasional X-ray sputters, but on this day, it did something unprecedented. Radio telescopes across the globe, including the Canadian CHIME experiment and the STARE-2 array in the United States, detected a furious, millisecond-long blast of radio waves erupting from its location. This was the fifth monumental discovery, the first fast radio burst ever detected originating from inside our own galaxy. The excitement was electric, a palpable shift in the field. For the first time, astronomers had caught a local burst, one so close its signal was millions of times brighter than any extragalactic counterpart. Crucially, space-based X-ray observatories were also watching, and they recorded a simultaneous, powerful X-ray burst from the exact same magnetar. This 1-2 punch of data provided the first direct smoking gun evidence. At least some fast radio bursts, perhaps the non-repeating kind, are indeed produced by magnetars. The event was like finally seeing a suspect caught in the act, confirming a theory that had been building for years. The magnetar, a city-sized neutron star spinning rapidly with a magnetic field 1,000 trillion times stronger than Earth's, had experienced a colossal starquake. This rupture on its unbelievably dense crust released a storm of energy across the electromagnetic spectrum, proving these objects are capable of generating the specific, intense radio flashes we see from across the universe. This local detection was a Rosetta Stone, translating the mysterious signals from deep space into a language of known physics. It confirmed we are dealing with some of the most extreme and volatile objects in existence, right here in our own cosmic neighborhood. The confirmation that magnetars could produce these bursts solved one mystery but amplified another, a paradox of almost impossible scale. Think about the energy released by our sun. It is a continuous nuclear furnace, bathing our solar system in light and warmth for billions of years. Now compress 80 years of that total solar output. Squeeze it down not into a day or an hour or even a second. Crush it into a flash lasting just a few thousandths of a second. That is the staggering, almost nonsensical power of a typical fast radio burst from a distant galaxy. It is the sixth and perhaps most humbling strange discovery. In the blink of an eye, a single cosmic event outshines our star's lifetime work. To frame it another way, the most energetic bursts we have detected release more energy in that millisecond than all of humanity will use in hundreds of centuries. This is not just a large number, it is a fundamental challenge to our understanding of physics. How does any object, no matter how extreme, focus that much raw power into such an impossibly brief and coherent signal? It would be like trying to channel the entire flow of every river on Earth through a single drinking straw, for less time than it takes for a camera's shutter to click. The cosmic engine responsible must be a master of efficiency and violence. Astronomers theorize it involves the unimaginably strong magnetic fields of a magnetar, trillions of times more powerful than anything we can create on Earth. A sudden crack in the star's crust, a magnetic reconnection event, could unleash a storm of charged particles. These particles, whipping around the magnetic field lines at nearly the speed of light, then radiate that focused beam of radio waves like a cosmic lighthouse on overdrive. The beam is so intense and so narrow that if you are not directly in its path, you would never know it happened. We only see them because the universe is so vast that a few of those deadly beams are inevitably pointed right at us. This revelation transforms the burst from a simple flash into a directed energy weapon of stellar proportions, a natural laser of incomprehensible power. What does it mean that such titanic, focused forces are at work in the quiet corners of dwarf galaxies, firing randomly into the dark? This public fascination with a powerful, unexplained radio signal is not new. Decades before the first fast radio burst was recognized, another enigmatic blip captured the world's imagination. In 1977, the Big Ear radio telescope at Ohio State University was scanning the sky for signs of extraterrestrial intelligence. One night, it recorded a signal so strong and so unusual that astronomer Jerry Amon circled it on the printout and simply wrote "Wow" next to it. The wow signal was a 72-second burst of radio waves, millions of times stronger than the background noise of space, and it appeared to come from a specific point in the constellation Sagittarius. It had all the hallmarks of an artificial, intelligent transmission, a beacon from the stars, yet despite decades of searching, it was never heard again. It became a ghost, a single tantalizing clue in the ultimate detective story. For years, the WOW signal stood as the best candidate for a message from another civilization, a symbol of our hope and our cosmic loneliness. Fast radio bursts, in their raw power and fleeting nature, are often seen as its modern successor in the public mind. Both are sudden, brilliant, and utterly mysterious screams in the radio static. This parallel is the seventh strange discovery, not about the bursts themselves, but about how they have reshaped our perspective. The existence of fast radio bursts provides a crucial new context. They demonstrate that the cosmos is naturally filled with incredibly powerful, transient, and highly focused radio phenomena that we are only beginning to understand. While the search for extraterrestrial intelligence continues with more sophistication than ever, fast radio bursts offer a compelling natural explanation for at least some types of mysterious signals. They have given scientists a new physical cosmic engine to study, a phenomenon born from the violent physics of magnetars and other extreme objects rather than from intelligence. This has subtly shifted the goalposts for SETI. Now, when a strange signal is detected, the first question is not always, is it them? Often it is, could this be a new type of fast radio burst? These cosmic flashes have become a benchmark for natural, yet astonishingly energetic radio events. They remind us that the universe is stranger than we imagined, capable of producing signatures so precise and powerful they mimic the very signals we might one day hope to receive. The sheer power of a fast radio burst is only half the story. Sometimes the main event is just the opening act. Astronomers have begun catching bursts that do not arrive alone. Instead, the brilliant millisecond flash is followed by something far stranger, a faint, lingering echo or a rapid-fire stutter of weaker signals. These are the side tones, the cosmic afterparty of a cataclysm, and they form our eighth strange discovery. Imagine hearing a single, deafening thunderclap, and then in the quiet that follows, you can still hear the rain gently pattering for several minutes. That is what telescopes like the 500-meter aperture spherical telescope, or FAST, in China have detected. For certain repeating bursts, the main powerful pulse is followed by a persistent, low-frequency murmur of radio waves that can last for up to an hour. This is not a simple echo. It is a continuous emission, a sign that the cosmic engine is not just cracking once and going silent. It is sputtering, releasing energy in a prolonged and messy aftermath. Other bursts arrive with what scientists call burst storms, where the primary flash is accompanied by a rapid series of dozens, even hundreds, of much weaker microbursts, all packed into a few minutes. These side tones are like listening to the source object cough and sputter as it recovers from its own violent convulsion. This chaotic tale of radio noise is a treasure trove of information. It tells us that the environment immediately surrounding the source is incredibly complex and turbulent. The leading theory points to a dense, swirling cloud of charged particles, a nebula created by the progenitor object, perhaps the stellar wind from a young magnetar. When the main burst erupts, it slams into this thick, magnetized soup. The initial shockwave creates the bright flash we see, but the energy then reverberates through this cloud, exciting particles and causing them to radiate for much longer at lower energies. The side tones are the sound of that energy dissipating, of the cosmic storm churning through its own debris field. By studying the duration and structure of these afterglows, astronomers can effectively map the weather around the source, estimating the density and magnetic chaos of a region we can never hope to visit. It transforms a single point of light into a dynamic, three-dimensional scene of cosmic violence and its messy cleanup. Just when the chaotic sputtering of side tones seemed to define the bursts, the cosmos delivered a shock of perfect order. In 2020, astronomers monitoring a known repeater designated FRB 180916 made a discovery so precise it felt almost artificial. This source, located in a spiral galaxy 500 million light-years away, was not just repeating, it was keeping time. It followed a strict 16.35-day cycle. For roughly 4 days, it would fire off bursts, sometimes several per hour. Then, like clockwork, it would fall completely silent for the next 12 days, only to wake up and begin the pattern all over again. This was the 9th strange discovery, a metronome ticking in the depths of space. The existence of such a clean, predictable periodicity was a revelation. In a universe dominated by chaos and explosive randomness, here was a cosmic engine with a schedule. It immediately ruled out purely random processes like simple starquakes on an isolated magnetar. Something had to be imposing this rhythm, acting as a cosmic conductor for the violent outbursts. The leading theory points to an orbital dance. Imagine the source, likely a magnetar, locked in a binary system with a massive companion star. As the magnetar orbits its partner every 16.35 days, there are specific points in that orbit where conditions are just right for bursts to be triggered. Perhaps the companion star blows a thick wind of gas, and when the magnetar plunges through this dense material, the interaction sparks the furious radio flares. The 4-day active window would then be the period when it is closest to or moving through that turbulent zone. Another compelling idea involves precession. A spinning neutron star can wobble like a top slowing down, its rotational axis slowly tracing a circle in space over time. If the burst-producing region on its surface is not at the equator, this wobble could aim its deadly beam toward Earth only during a specific phase of that precession cycle, creating the regular window of activity we observe. A third possibility is a debris disk, a shroud of material left over from the star's explosive birth or torn from a companion could surround the magnetar. This disk might periodically obscure our view, or its own gravitational influence could modulate the release of energy from the star below. This 16-day clockwork does more than deepen the mystery, it gives astronomers a powerful tool. They can now predict when the source will be active, pointing the world's most sensitive telescopes at it in advance, ready to capture every detail of its outbursts. This regularity feels eerily familiar, a natural pulse in the cosmos that echoes the orbital rhythms of our own solar system. It whispers that even the most violent events might be choreographed by the gentle, predictable laws of gravity. That precise 16-day rhythm is a powerful clue, but the signal itself carries an even more specific fingerprint. When astronomers dissect the light from a fast radio burst, they often find it is not just a simple flash of radio noise. It is highly polarized, meaning the electromagnetic waves are all vibrating in a specific, organized pattern rather than chaotically in every direction. This is our 10th strange discovery, and it acts like a cosmic forensic tool, revealing the brutal environment the signal endured on its journey to us. Think of polarization like light passing through a pair of sunglasses. The lenses filter out all the light waves except those oscillating in one particular orientation. The radio waves from many fast radio bursts arrive at our telescopes in a similar state, as if they have been filtered by the universe's most extreme pair of shades. There are two main types of this organized light. Linear polarization means the waves are all vibrating in a single plane, like a rope being shaken strictly up and down. Circular polarization means the wave's orientation rotates as it travels, spinning like a corkscrew through space. The key is that ordinary space does not create this effect on its own. For a signal to become this highly polarized, it must have passed through an environment with an incredibly powerful and ordered magnetic field. This magnetic field acts like a cosmic comb, brushing all the radio waves into the same precise alignment. The detection of extreme polarization, especially a type called 100% linear polarization, is a direct and screaming signature. It tells us the burst was born in or passed very near a region of mind-bending magnetic fury. The prime suspects for creating such conditions are immediately narrowed down to the most magnetically charged objects in existence. Magnetars with their trillion Gauss fields are the perfect candidate. Their immediate surroundings are a maelstrom of organized magnetic force, perfectly capable of imprinting this polarized signature on any radiation escaping their grasp. The other contender is the violent neighborhood around a black hole, where magnetic fields can be amplified to unbelievable strengths in the swirling accretion disk of doomed matter. This polarization clue is like finding a piece of shrapnel magnetized by a bomb blast. It points unequivocally back to the weapon that created it. So when we catch a highly polarized burst, we are not just seeing a flash of light. We are reading a magnetic barcode scanned across billions of light years that spells out one word: magnetar. That magnetic barcode is only the first part of the message. To read the full story, you need to see how it changes. The 11th strange discovery involves a subtle twist in the signal, a phenomenon called Faraday rotation. It is a cosmic detective trick that reveals not just the presence of a magnetic field, but its strength and even the density of the material the signal traveled through. Imagine you are holding a rope and you begin to shake it up and down, creating a vertical wave. Now, imagine passing that rope through a special twisting tunnel. By the time the rope emerges on the other side, the wave might be vibrating horizontally or even spinning. Faraday rotation does exactly this to polarized radio waves. As the signal travels through a magnetized plasma, a soup of charged particles and magnetic fields, the plane of its polarization slowly rotates. The stronger the magnetic field and the denser the plasma, the more the signal twists. It is like the cosmos itself is turning a dial on the signal's orientation during its billion-year journey. When astronomers measured the Faraday rotation for the famous repeater, FRB 121102, the numbers were off the charts. The signal was twisted by an enormous amount, far greater than what we see from most other cosmic sources. This massive rotation is a direct and powerful clue. It tells us the burst did not just pass through the weak, diffuse magnetic fields of intergalactic space. Instead, it must have originated deep within an environment of incredible magnetic intensity. The signal was imprinted with this extreme twist right at its source or in the dense, magnetized nebula immediately surrounding it. This observation is like finding a piece of metal that is not just magnetized but warped and twisted by the very forces that magnetized it. It points the finger once again at the universe's ultimate magnetic monsters. Only a magnetar, or perhaps the turbulent region around a newborn black hole, possesses the kind of ferocious magnetic environment needed to cause such an extreme Faraday rotation. This magnetic fingerprint is now a standard tool. When a new burst is detected, measuring its Faraday rotation gives astronomers an instant estimate of the hellish magnetic conditions it endured, bringing us one step closer to visualizing the invisible fury at the heart of these brilliant flashes. These magnetic fingerprints do more than identify the source. They turn the burst itself into a precision instrument for mapping the cosmos. This leads us to the 12th strange discovery, one that flips the entire mystery on its head. Fast radio bursts are not just puzzles to be solved, They are powerful new tools for solving one of cosmology's greatest riddles, the case of the missing matter. You might think we have a good inventory of the universe. We can see the stars, the galaxies, the vast clouds of gas in nebulae. But when cosmologists tally up all this normal matter, the kind made of protons and neutrons that builds everything we can touch and see, they come up short. A staggering 30 to 40% of it is simply missing from our cosmic ledger. This is the missing baryon problem. This matter is not dark matter. It is the ordinary atoms that should be there but have seemingly vanished. The leading theory is that it exists in a form incredibly difficult to detect, as a diffuse, superheated fog of ionized gas strewn in the vast voids between galaxies. This gas is so thin and so hot it emits almost no light we can capture, making it virtually invisible to traditional telescopes. This is where fast radio bursts become revolutionary probes. Remember the dispersion, that telltale stretch in the signal caused by electrons in space. That is not a flaw, it is a feature. Every electron the signal passes through adds a tiny, measurable delay to the lower frequencies. By carefully measuring the total dispersion of a burst, astronomers can literally count the total number of free electrons along its entire path from the source galaxy to Earth. It is like using the burst as a cosmic dipstick. We know how far the burst has traveled from its host galaxy. By subtracting the expected contribution from the gas within that galaxy and within our own Milky Way, what remains is a direct measurement of the ionized material in the intergalactic medium, the very place the missing baryons are hiding. With each new burst detected from a different distance and direction, we get another sample, another measurement of the cosmic fog. Early results from cataloging many bursts are incredibly promising, suggesting that this warm, hot intergalactic medium does indeed contain enough material to finally account for the universe's missing normal matter. In this way, a mysterious flash from a dying star becomes a beacon that illuminates the invisible scaffolding of the cosmos itself, helping us complete a fundamental inventory of all that exists. Gravitational lensing is one of the universe's most elegant tricks, a prediction of Einstein's theory where massive objects warp the very fabric of space-time. This curvature acts like a cosmic magnifying glass, bending and distorting the light from objects behind it. We see this with galaxies and quasars, their images stretched into brilliant arcs and rings around foreground galaxy clusters. Now, astronomers are asking a thrilling question: could a fast radio burst be lensed? This is the 13th strange discovery, a theoretical frontier that could turn these fleeting flashes into the sharpest tools yet for mapping the invisible. The concept is breathtaking in its potential. Imagine a burst erupts from a distant magnetar billions of light years away. On its journey to Earth, its path passes near a massive intervening object, perhaps a single galaxy or even a solitary black hole drifting in the void. The gravitational field of this object would split the burst signal. Instead of one flash, our telescopes would record 2, 3, or even 4 identical bursts arriving at slightly different times. They would be perfect echoes, the same complex fingerprint of polarization and dispersion, but staggered by microseconds or milliseconds. This time delay is the critical clue. It is a direct measure of the mass of the lensing object, including all the dark matter it contains. Because a fast radio burst is so brief and coherent, the lensing measurement would be exquisitely precise, far sharper than what is possible with the smeared, extended light of a galaxy. It would be like using a strobe light instead of a light bulb to measure the shape of a lens. The hunt is on for these cosmic echoes. Detecting a lensed fast radio burst would be a monumental achievement, opening a new window on cosmic structure. It could allow us to weigh isolated black holes or map the distribution of dark matter in individual galaxies with unprecedented accuracy. More speculatively, if the lensing object were small and dense enough, like a star-sized clump of dark matter, The multiple images could be separated by years, not milliseconds, creating a repeat burst pattern with a delay we could never explain with orbital mechanics alone. While no confirmed lensed burst has been found yet, the search itself reframes what these signals can do. They are no longer just messages from violent engines, but potential precision beams that illuminate the warped geometry of the cosmos itself, revealing the heavy, unseen hands that bend their paths. Distance records in astronomy are made to be broken, but some shatter all expectations. In June of 2022, a flash designated FRB 202-20610 erupted into the data streams of the Australian Square Kilometre Array Pathfinder. Its dispersion measure was staggering, the highest ever recorded, pointing to an origin almost impossibly far away. Calculations placed its source at a redshift of 1.0, meaning the light from this burst had been traveling for over 8 billion years. It was a signal from when the universe was only 5 billion years old, a cosmic toddler in the grand timeline. This 14th discovery was not just about a new distance champion, it was a message from a radically different era of cosmic history. The sheer power required for this flash to reach us across such a gulf is almost beyond comprehension. The burst released the equivalent of 30 years of our sun's total energy output in a single millisecond. Detecting it means the engines powering these events were not only active in the early universe, they were operating at a staggering, perhaps even greater, peak efficiency. The universe 5 billion years after the Big Bang was a more compact, more chaotic, and more fertile place. Star formation rates were at their cosmic peak, with galaxies colliding and merging, creating vast stellar nurseries. This environment was a perfect breeding ground for the short-lived, massive stars whose violent deaths create magnetars. The existence of such a powerful burst from this epoch tells us that the conditions to forge these extreme objects and to trigger their catastrophic outbursts were present very early on. It suggests that fast radio bursts are not a modern cosmic phenomenon, but a fundamental feature of a violent, adolescent universe. This single flash is a time capsule, proving that the universe's most magnetic monsters were already screaming into the void, lighting up the cosmic dark with a fury that we are only now beginning to perceive. That record-breaking flash from the early universe forces a difficult question. If these bursts can erupt from anywhere and anyone, is there a typical home for them? The answer is a resounding and confusing no. This is the 15th strange discovery, a profound lack of consistency in the neighborhoods that host these cosmic sirens. We have traced them to tiny, chaotic dwarf galaxies, the cosmic equivalent of rural workshops. We have found them in grand spiral galaxies like our own Milky Way, the bustling metropolises of the universe. Most recently, and perhaps most puzzlingly, a repeating burst was pinpointed to an ancient globular cluster, a dense ball of stars that formed over 10 billion years ago and contains almost no raw material to create new ones. This is a staggering range of environments. A dwarf galaxy is a fertile, messy stellar nursery, rich in the basic hydrogen and helium from the Big Bang. A spiral galaxy is more mature and organized, with heavier elements scattered from generations of supernova. A globular cluster is a retirement home for ancient stars, a place where star birth ceased eons ago. The fact that fast radio bursts emerge from all three tells us something crucial. There cannot be just one single recipe, one exclusive set of ingredients required to cook up these events. It suggests that the underlying engine, likely a magnetar, can be forged through multiple cosmic pathways. Perhaps in dwarf galaxies, it is the direct collapse of a massive, short-lived star. In spirals, it might be the merger of two white dwarfs or the evolution of a highly magnetic star in a binary system. In that ancient globular cluster, the magnetar could be the extremely rare product of two neutron stars colliding, a relic of a violent dance that happened billions of years ago in the cluster's crowded core. This environmental diversity is a liberating and complicating clue. It means the universe is more creative than we imagined, finding multiple ways to build and trigger its most powerful radio transmitters. The search for a single host galaxy type is over, replaced by a new mystery: how many different roads lead to the same cataclysmic destination? This environmental diversity points to a deeper question about the engine itself. What keeps it running? For some repeaters, the answer appears to be a permanent power source. The 16th strange discovery is that certain bursts are not alone in the sky. They are anchored to a persistent, steady glow of radio waves. The most famous example is the original repeater, FRB 121102. Alongside its sporadic millisecond fireworks, telescopes detected a faint but constant radio source, always there, humming in the background. It is as if the brilliant flash of a camera is coming from a room where a lamp is always left on. This co-location is a major clue, a sign that the burst source is embedded within a larger, more permanent structure. This persistent radio source is not just noise. It is a reservoir, a clue to the long-term environment that fuels the repeating explosions. Astronomers have several compelling theories for what this steady glow could be. The leading idea is a magnetar wind nebula. Picture the magnetar as a furious, spinning dynamo, constantly blowing out a storm of high-energy particles. This wind slams into the slower-moving debris from the star's original supernova explosion, or into the surrounding interstellar gas. The collision creates a swirling, magnetized bubble of particles that glow steadily in radio waves. Within this nebula, conditions are perpetually tense, a pressure cooker of magnetic energy. When the magnetar on its surface cracks in a starquake, the released energy can funnel through this nebula, perhaps focusing it into the incredibly sharp beam we see as a burst. The nebula acts as both a power supply and a lens. Another possibility is that the persistent source is a jet from an active galactic nucleus, a supermassive black hole at the galaxy's center. But FRB 121102 lies in a tiny dwarf galaxy, and its position is offset from the galactic center, making this less likely. A third candidate is a young supernova remnant, the expanding shell of a recent stellar explosion, still glowing hot from the blast. This would fit the youthful, chaotic environment of a star-forming dwarf galaxy. The presence of this steady companion transforms our view. It means the repeating burst source is not an isolated, lonely object occasionally misfiring. It is part of an ecosystem, a violent heart at the center of a storm that never fully calms. The persistent radio source is the signature of that ongoing storm, the environment that stores the energy and perhaps even dictates when and how the magnetar unleashes its next cataclysmic scream. The persistent hum of a cosmic engine is one thing, but a signal that arrives precisely at Christmas feels almost like a cosmic prank. In October 2001, the Parkes Radio Telescope in Australia recorded a strange event. It was a bright, dispersed burst, similar to the now famous Lorimer burst that will be discovered 6 years later. But this one, catalogued as FRB 011025, had a peculiar detail. It occurred at a time when a known source of human-made radio interference, a puritan, was also active at the site. Puritans are frustrating mimics. They are short, dispersed radio bursts that look, at first glance, exactly like cosmic fast radio bursts. But they are not from space. They are created by human technology, often from malfunctioning electronics, microwave ovens, or even passing aircraft, their signals reflecting off the ground and into the telescope's sensitive receivers. Because of its timing and properties, the October 2001 burst was dismissed. It was filed away not as a discovery, but as contamination, another puritan polluting the data. For over a decade, it languished in the archives, a ghost written off as garbage. This is the 17th strange discovery, a tale of human error and cosmic patience. Years later, as the catalogue of genuine fast radio bursts grew, scientists revisited old data with new, more sophisticated analysis tools. They took another, harder look at that October event. The reanalysis revealed something startling. Its signal characteristics did not perfectly match the profile of the known Puritan interference at Parkes. The shape of its burst, the way its frequencies were dispersed, seemed subtly different, more consistent with a signal that had traveled through a vast amount of cosmic plasma. The evidence was not conclusive, but it was compelling enough to reopen the case. FRB 011025 was rebranded, tentatively, as the Christmas burst, a potential genuine fast radio burst that had been hiding in plain sight, masquerading as human noise. This story highlights one of the most profound and ironic challenges in modern astronomy. Our planet is now drowning in its own radio chatter. From satellites and cell phones to radar and everyday appliances, we have wrapped Earth in a shimmering shell of radio noise. Distinguishing a true cosmic scream from this terrestrial cacophony is a detective's nightmare. A Puritan and a fast radio burst can look like identical twins in the data. The only way to tell them apart is through meticulous forensic work, checking the signal's polarization, its exact frequency structure, and whether multiple telescopes in different locations saw it at the same instant. A true cosmic burst will be seen across a continent, while a local Puritan will only affect one telescope. The Christmas burst reminds us that our search for cosmic wonders is now a constant battle against our own technological reflection. It asks a humbling question: how many other genuine signals from the depths of space have we already recorded, only to delete them as mere static from a faulty microwave oven? The ancient globular cluster seemed an impossible home for such a violent event. These dense, spherical swarms of stars are the universe's retirement communities, filled with stellar populations over 10 billion years old. They are quiet, stable places where star formation ceased eons ago, and the massive, short-lived stars that typically collapse into magnetars have long since burned out and disappeared. That is why the 18th discovery sent such a profound shock through the astronomical community. A repeating fast radio burst known as FRB 20201124A was pinpointed with incredible precision not just to a distant spiral galaxy, but to a specific, ancient globular cluster on its outskirts. It was like finding a roaring jet engine inside a library reading room. This environment directly contradicts the leading model. How could a magnetar, a product of a recent, violent stellar death, exist in a place where all the ingredients for such a star vanished billions of years ago? This paradox forces a radical rethink of the cosmic pathways that can lead to a fast radio burst. Astronomers are now exploring origins that thrive in extreme density rather than extreme youth. In the crowded core of a globular cluster, stars are packed 1,000,000 times more tightly than in our solar neighborhood. In this stellar traffic jam, close encounters and collisions are not just possible, they are inevitable over billions of years. One compelling alternative is a collision between two white dwarfs, the Earth-sized embers of dead sun-like stars. If two of these dense cores spiral together and merge, the resulting explosion could forge a neutron star in a single, catastrophic event, bypassing the need for a recent supernova from a massive star. Another possibility is the merger of two neutron stars already present in the cluster. An event we know produces gravitational waves and can result in a new, highly magnetized neutron star or a black hole. A third, even more exotic idea involves a neutron star and a white dwarf in a tight binary system. The neutron star could slowly siphon material from its companion, a process that spins it up and potentially rejuvenates its magnetic field, turning it into a magnetar-like engine through theft rather than a fresh birth. This discovery in the globular cluster is a powerful reminder that the universe always has more than one recipe for cosmic violence. It proves that the conditions for creating these brilliant flashes can be preserved or even manufactured anew in the most ancient and seemingly tranquil corners of galaxies. The burst is not a sign of youth, but a ghost of past collisions, a scream from a dense stellar graveyard that found one last way to make its presence known. The universe's most precise cosmic clock sometimes plays a melody. For the repeater known as FRB 202209128, astronomers noticed its individual bursts were not just random clicks. They were changing pitch. Each time this source fired off a salvo of bursts during its active period, a fascinating pattern emerged. The center frequency of each successive burst drifted steadily lower. It began with a high, sharp note and ended with a deep, low hum, like a sliding whistle being extended or the descending glissando of a sad trombone. This 19th discovery is a subtle fingerprint in the noise, a clue that the environment around the source is dynamic and layered. The leading explanation for this downward drift involves the signal traveling through a shroud of plasma, a hot soup of charged particles that surrounds the central engine. Imagine this plasma as a dense, turbulent fog with varying density. Higher frequency radio waves can punch through the outer, thinner layers more easily. But as the source continues to erupt, perhaps with each burst excavating a path or the plasma itself churning and moving, the later signals are forced to travel through slightly different or even thicker inner regions of this fog. These deeper layers slow down the higher frequencies more effectively, so what finally escapes and reaches us is shifted toward lower and lower tones. It is as if we are listening to the burst tune itself by moving through a cosmic filter that is constantly adjusting. This drifting whistle tells a story of change near the source in real time. It suggests the magnetar is not sitting in a static cavity, but within a nebula that is reacting to its outbursts, a storm where each lightning strike alters the atmosphere for the next. By decoding this simple slide in pitch, we are essentially hearing the weather report from a region of space a billion light-years away, where the air itself is made of magnetized fire. That drifting whistle is a signature of a unique personality, and this is the critical 20th discovery. Not all repeaters are the same. They are a diverse cosmic family, each with its own distinct character, suggesting we may be observing different types of engines or different chapters in a violent life story. Take the original repeater FRB 121102. It is prolific and chaotic, a cosmic machine gun. It fires off bursts in frenzied clusters, sometimes dozens in an hour with no apparent rhythm. It is also the one famously linked to a persistent radio source, a constant hum from its surrounding nebula. This repeater feels like a young, unruly beast still embedded in the energetic wreckage of its birth, firing almost at random as it settles into its power. Then there is the clockwork repeater FRB 180916. It is the epitome of order. Every 16.35 days, it wakes up for a 4-day active window, fires its burst, and then goes quiet. Its bursts are less frequent and more predictable. This source feels like an older, more settled system, perhaps one locked in a precise gravitational dance with a companion star, its outbursts regulated by the tides of its orbit. And there are others. Some repeaters have no detectable persistent glow at all, their bursts erupting from seeming emptiness. Some have shown downward frequency drifts in their bursts, while others have not. This diversity is a powerful clue. It tells us that the simple label repeater is not enough. We are likely witnessing different phenomena, or the same phenomenon in different environments and stages of evolution. A young magnetar, freshly born in a supernova and surrounded by a dense nebula, might behave like the chaotic repeater. An older magnetar in a binary system might be tamed into the periodic one. Some bursts might even come from a different engine entirely, like an exotic type of pulsar or a black hole accretion event. The variety in the repeaters themselves is a message. It whispers that the universe has more than one way to build a cosmic siren, and we are only beginning to learn the different songs they can sing. The distinct personalities of repeaters offer clues, but to truly understand the engine, we need to see it with more than just radio eyes. This brings us to the 21st strange discovery, a search that has largely seen astronomers staring into an empty sky. Around the world, when a fast radio burst alert sounds, a coordinated scramble begins. Optical telescopes swing into position, hunting for a flash of visible light. X-ray and gamma-ray observatories, both on the ground and in space, scan the same coordinates, seeking the high-energy signature of a cataclysm. The goal is to catch the burst across the entire electromagnetic spectrum, to see its full fury revealed in every color of cosmic light. Yet, with one monumental exception, these campaigns have found almost nothing. Aside from the simultaneous X-ray burst from our own galaxy's magnetar, no definitive counterpart in visible light, X-rays, or gamma rays has ever been linked to an extragalactic fast radio burst. The radio flash arrives brilliant and isolated, and then there is only silence in all other wavelengths. This profound emptiness is a puzzle that cuts to the heart of the phenomenon. If these events truly release the energy of 500 million suns, where is all that power going? The most compelling answer is one of astonishing efficiency. It suggests the cosmic engine is not a messy, all-directional explosion like a supernova. Instead, it is a precision instrument, a natural laser that focuses almost all of its catastrophic energy into a narrow beam of coherent radio waves. Think of a lighthouse whose entire bulb is engineered to produce only a specific shade of deep red light, with almost no waste heat or visible glow. The physics of a magnetar starquake or a magnetic reconnection event might be uniquely suited to this, channeling the fury of the crust's rupture directly into accelerating particles along magnetic field lines, which then radiate predominantly at radio frequencies. The alternative is a problem of timing. The multi-wavelength flash might be incredibly brief, even shorter than the radio burst itself, or it might arrive at a slightly different time if it originates from a different part of the complex event. Our telescopes, for all their power, might simply be blinking at the wrong millisecond. This great silence in other wavelengths is not a failure, it is a directive. It tells us that whatever creates these bursts is a specialist, a master of focused radio violence, leaving the rest of the cosmic spectrum dark as it fires its impossible beam across the universe. That great silence in other wavelengths is a blank canvas for the imagination. With each new strange property discovered, the list of possible explanations has exploded, running the gamut from established physics to the edges of science fiction. This 22nd discovery is not a single finding, but a tour through the wild spectrum of theories trying to explain the impossible. At the forefront, with the most evidence, stands the flaring magnetar. It fits so many clues: the polarization, the Faraday rotation, the local galactic detection. A starquake on this hypermagnetized neutron star could focus a beam of energy along its magnetic poles, creating the brilliant, coherent flash we see. It is a violent but natural engine, one that can survive to repeat, but the universe is rarely so simple. Other exotic natural ideas push the boundaries. Could they be produced by cosmic strings, hypothetical defects in the fabric of space-time left over from the Big Bang? If these strings vibrated or snapped, they might release tremendous energy in bursts. Or perhaps they are signs of primordial black holes, tiny remnants from the universe's first second, finally evaporating in a final burst of Hawking radiation. Some theorists have proposed collisions between dense objects we have yet to imagine, like asteroid-sized chunks of strange matter striking a neutron star. Each idea attempts to account for the staggering energy and brief duration, but few can easily explain the repeating patterns or the diverse host galaxies. Then, of course, there is the hypothesis that captures the public imagination most fiercely. Could they be artificial? Could fast radio bursts be the leakage, or perhaps the deliberate signals, of an advanced technological civilization? Astronomer Avi Loeb has famously speculated that such powerful, focused beams could be used for interstellar propulsion to push light sails on spacecraft across the galaxy. A burst aimed at a sail could transfer immense momentum, a kind of cosmic push start for voyages between stars. From this perspective, the repeating pattern might be a beacon, or the side effect of a propulsion system turning on and off as it targets different destinations. It is a thrilling idea, but the scientific consensus leans heavily toward natural causes. The reason is Occam's razor, the principle that the simplest explanation is usually best. Magnetars are proven to exist. We have seen one produce a burst, and their physics can theoretically create the signal we observe. An alien civilization is an extraordinary claim requiring extraordinary evidence, and so far, every strange property of the burst has found a potential natural explanation. Yet, the very act of considering such a wild idea serves a vital purpose. It forces us to question our assumptions and reminds us that in a universe this vast and old, the line between natural phenomenon and technological artifact might one day astonishingly blur. The search for these cosmic sirens was once a painstaking hunt, relying on luck and single telescopes staring at tiny patches of sky. That all changed with a revolutionary new instrument in the mountains of British Columbia. The Canadian Hydrogen Intensity Mapping Experiment, or CHIME, is not a conventional dish that swivels and points. It is a fixed array of 4 half-cylindrical reflectors, each as long as a football field, lined up like giant snowplows facing the sky. Its design is its genius because it does not move. It sees a vast strip of the heavens every single day as the Earth rotates. It is the ultimate cosmic net, cast wide to catch the fleeting flashes that other telescopes would almost certainly miss. This 23rd discovery is not about a single burst, but about a fundamental shift in scale. Before CHIME, fast radio bursts were rare gems with perhaps a few dozen confirmed. Since it began full operations, CHIME has detected thousands. It has turned a trickle of data into a flood, transforming these events from exotic anomalies into a statistical population we can finally analyze. We are no longer just collecting mysterious specimens. We are studying the behavior of an entire species. The telescope's wide field view allows it to catch repeaters with unprecedented efficiency, building up catalogs of their activity patterns. It has found bursts with every conceivable dispersion measure, probing different cosmic distances and environments. This torrent of data is the raw material for a new kind of science. Astronomers can now ask questions that were impossible before. How are bursts distributed across the sky? Is there a typical energy distribution? Do repeaters and one-off bursts come from fundamentally different populations? CHIME Relentless Scan provides the numbers to begin answering these questions, turning the philosophical mystery of the bursts into a rigorous field of astrophysical census-taking. The revolution is not just in quantity, but in consistency. With a single instrument monitoring so much of the sky, we finally have a uniform dataset, free from the biases of different telescopes with different sensitivities. It is as if we have switched from listening for thunderclaps with a single, directional microphone to monitoring the entire hemisphere with a grid of sensitive barometers. The storm of fast radio bursts, it turns out, is a constant, gentle rain across the cosmos, and CHIME is the first instrument built to measure its true downpour. That flood of data from telescopes like CHIME offers more than just a catalogue of mysteries. It offers a potential key to unlocking the universe's deepest secrets. This brings us to the 24th and perhaps most profound strange discovery on the horizon. Fast radio bursts might one day become cosmic standard candles, or more accurately, standard sirens. The concept is breathtaking in its ambition. In cosmology, a standard candle is an object of known intrinsic brightness. By measuring how dim it appears from Earth, you can calculate its distance, the same way you can judge how far away a car is at night by the fading glow of its headlights. For decades, astronomers have used specific types of supernova for this, building the cosmic distance ladder that revealed our expanding universe. But this method has pitfalls and relies on a chain of assumptions. Fast radio bursts could offer a cleaner, more direct route. The key lies in that dispersion measure, the total stretch of the signal caused by electrons in its path. If we can independently determine exactly how much of that dispersion comes from the intergalactic medium alone, subtracting the contributions from the host galaxy and our own Milky Way, then the remaining value gives us a direct measure of the total amount of cosmic stuff the signal traveled through. And because the density of the universe decreases in a predictable way as it expands, that measurement translates directly into a distance. It would be like hearing a siren and knowing exactly how much fog lies between you and the source, thereby knowing precisely how far away it is. The challenge is immense. We need to perfectly understand the messy environments near the burst source and in its host galaxy to make that subtraction. But if we can calibrate this method, perhaps by linking a burst to a galaxy with a distance measured by other means, the promise is revolutionary. These flashes could become independent probes of the universe's expansion rate, the Hubble constant. Even more thrilling, they could trace the large-scale structure of the cosmic web, mapping the invisible filaments of dark matter and gas that connect galaxies. Each burst becomes a single, brilliant data point, illuminating not just its source but the vast, empty highways it traveled. In this future, a fast radio burst is no longer just a message from a monster. It is a flare shot into the cosmic fog, and by measuring how that fog dims its light, we might finally measure the force that fills the void, the mysterious dark energy that is pulling our universe apart. But the final and perhaps most humbling discovery brings us full circle to a flash that defies both distance and time. In 2023, the same ASCAP telescope that found the distance champion just a year earlier detected something even more extraordinary. A burst designated FRB 202200610 was not just far, it was ancient. Analysis revealed its light had been traveling for 8 billion years. This signal erupted when the universe was a mere 5 billion years old, less than half its current age. That single millisecond of radio noise is a fossil, a direct message from the cosmos's tumultuous youth. Its existence is a staggering revelation. It proves that the engines capable of such focused violence were not a later development in cosmic history. They were already operating at peak, universe-shaking efficiency when the first galaxies were still taking shape. This pushes our understanding of stellar evolution to the absolute limit. To create a magnetar, you need a massive star that lives fast and dies young. In the early universe, the first generations of stars were composed almost entirely of hydrogen and helium, the pristine elements forged in the Big Bang. These population 3 stars are theorized to have been monsters, hundreds of times more massive than our Sun, burning fiercely and collapsing in spectacular supernova. The detection of this 8-billion-year-old burst suggests these primordial giants could indeed forge the intensely magnetized neutron stars required. Or it reveals that other, even more exotic pathways to these cosmic engines existed in the dense, chaotic nurseries of the young cosmos. This oldest flash is not just a record breaker. It is a boundary post. It tells us that for as long as the universe has been building stars and galaxies, it has also been punctuating the darkness with these brilliant, impossible screams. The mystery of fast radio bursts is not a modern puzzle. It is as old as the stars themselves, written in radio waves across the vast expanse of cosmic time, waiting for us to finally learn how to listen. From a single ghost in the data to a chorus of cosmic sirens, the story of fast radio bursts is a testament to how one strange signal can rewrite our understanding of the universe. We began with a solitary spike of radio noise, a 5-millisecond anomaly that challenged belief. Today, we stand before a vibrant field of astronomy, a detective story woven from 25 profound discoveries. These fleeting flashes have evolved from a mere curiosity into a revolutionary tool, connecting the violent deaths of stars to the invisible scaffolding of the cosmos itself. They have forced us to confront cosmic engines of impossible power, to map the universe's missing matter, and to listen for the rhythmic heartbeat of distant, magnetized monsters. The journey has taken us from chaotic dwarf galaxies to ancient stellar graveyards, proving that the universe holds more paths to violence than we ever dreamed. This is no longer just astrophysics, it is a new lens on cosmology, particle physics, and the fundamental architecture of reality. The next chapter promises even greater revelations. Instruments like the upcoming Square Kilometre Array, a global network of antennas with unimaginable sensitivity, will soon scan the skies. It will detect tens of thousands of new bursts every single day, turning our gentle rain of data into a torrential downpour. With that flood will come answers and undoubtedly new questions we cannot yet conceive. Which of these 25 discoveries left you in the greatest awe? Was it the precise 16-day clockwork of a distant repeater, or the humbling power of a flash outshining our sun for 80 years? Share your thoughts in the comments below, and if you are captivated by the mysteries hidden in the cosmic dark, subscribe for more journeys to the edge of understanding. The universe is still whispering its secrets, and we are only just beginning to hear.